Hi everyone. In today's video, we'll be talking about a priority queue. So what is a priority queue? So priority queue is a data structure where you can find the minimum very quickly. But then you can say that why do I need another data structure for that? I can just have a sorted array where I can find the min very quickly, which is true. You can find the min in constant time in a sorted array. The difference is in priority queue, you can remove min and you can add items, all of it in log n. So if you have an application where you need to remove the min and or may also maybe have to add more items and you want it all to be fast, then you will use a priority queue because both insert and remove min for a priority queue is log n. For a sorted array, if you have to insert, you have to find the item and move all the items to make space for to insert that item, which makes the insert to be big O of n. So that is where you use a priority queue where you want fast insert, fast remove min, and find min should be fast. So real life application of this is in Dijkstra's algorithm. So in Dijkstra's algorithm, there is this use case where you need to find the next closest destination to the source. So you find the next closest destination, remove it from the queue, then you find the next closest destination to the source, remove it from the queue. So that is one place of the many where priority queue lends itself ideally. So priority queue itself is abstract. One implementation of it is called a binary heap. So the way you do a binary heap implementation of a priority queue is by following these rules. So the first three rules makes it a complete binary tree, and then on top of that there is this additional property that the child's key has to be bigger than the parent key, or the parent key has to be smaller than the child key, smaller than or equal to the child key. So let's look at an example that will make it easier. So first let's look at complete binary tree. So every row has to be filled left to right. So this way. If you have it this way, this is not correct because it has to be filled left to right. So it has to be filled like this, and every row has to be full except the bottom row. Bottom row can or cannot be full, that's fine. But every row has to be full. So if I do this way, this row is not full, right? So then again that's not allowed because every row has to be full except for the bottom row. Rows have to be filled left to right, and every node has two children. So it's pretty simple. Basically this is a complete binary tree. This is also a complete binary tree. So to make a binary heap, you have to have a complete binary tree, and on top of that you need that parent has to be smaller than the child. Actually parent has to be smaller or equal to the child, but easier way to remember is parent is smaller than the child. So if you have 3 here, this can be 6, so this can be 6, this can be 9, this is correct. It's we are still meeting the property. If we do here 10, here 15, so this is like a binary heap where everywhere the parent is smaller than the child, parent smaller than the child, parent smaller than the child, parent smaller than the child. So the smaller one goes up compared. So this can be bigger than this one, doesn't matter, you just compare it to the parent. So this has to be like 99. If I put here, that's still correct because parent has to be smaller than the child. So that is a binary, how you create a binary heap. But you don't have to do it in using a tree data structure. Like you don't need to do it. So this is the visual representation of a binary heap, but you won't actually be using, or you can, but you don't have to have a tree node and the left child and the right child. There is a more efficient implementation of it where you use an array. So the way it works for an array is that, say you have a tree like this. So one way, so this is a binary heap where parent is smaller than the child and it's a complete binary tree. One way to do this is you can actually use a node, left child, right child, parent pointer. But the more efficient way to do this is by using an array. So you can use an array where you use indexes to find the children. So the way to do it is you leave the first index empty. Say this is index 0, it's empty, and then you start filling from here. So this will be index 1, this is index 2, index 3, index 4, index 5. So let's look at it. So 3 will go at index 1, then you have 6, 9, and then you have 15, 21. And say there is rest of the array is empty. So the way you find parent child is looking at the index. So this is 1, 2, 3, 4, 5. So sorry, let me put index in a different color so that will make it easier to understand. So the red color is the index 0, 1, 2, 3, 4, 5. So the way this works is that the child is 2 times index and 2 times index plus 1. So what I mean by that is the child for this one, index 1, is 2 times the index, which is 2, and 2 times the index plus 1, which is 3. So let's see, child for 3 is 6 and 9. If you look here, child for 3 is 6 and 9, correct? Now suppose I want to find the children of this guy. So this guy's children are 3 2s are 6 and 6 plus 1 7. Those are empty. So 9 has no children, which is correct. Now say 6. This guy's children are 2 2s are 4, which is this, plus 1 5. So 6 children are 15 and 21. 15, 21, 4. See? So that's how you do it. You just use an array and use index mathematics, just do mathematics on the index to find the parent child. So this is how you find the child. To find the parent, what you do? You do the divide by 2 and convert that to an integer, or you can say the floor of that number. So say for index 5, 5 divided by 2 is 2.5 and the integer of 2.5 is 2. So this guy's parent is at index 2, which is here. So let's see, 21 parent is 6. See? So that's how you do it. So child is 2 times the index and 2 times the index plus 1, 2 children. Parent is index divided by 2, the integer of it. So now let's see what is the way to construct a binary heap. So suppose we insert these numbers. First you insert 10. Okay, so the first will be straightforward at 10. Okay, then again remember, this is just a representation. Actually you are just doing it in an array where you add it at the appropriate index and swap it from at the appropriate index and remove it from the appropriate index. So first you insert 10, next I insert 100. So every time you insert, the way to do it is something called a bubble up. So the way it works is you put it at the last position and then you compare it to its parent, and if the parent is bigger, you swap it with the parent. So I insert 100 here. Next is 20. Complete binary tree has to go this way, 20. Compare it with the parent. Is the parent bigger? No, parent is smaller. So this is still correct. Don't do anything. 35. Complete binary tree, put it here 35. Now here, note that this condition is not met. The parent has to be less than the child key. Compare it with the parent, parent is not less. I swap it. So this becomes 35 and this becomes 100. Compare with the parent again. Parent has to be smaller. Parent is small, leave it alone. Next number, number 6. Insert it at the end. Compare with the parent. Parent has to be smaller. So swap. 6, 35. Compare it with the parent. Parent has to be smaller. Swap. 6, 10. Okay, now we are done. Next number, number 17. Insert it here. Compare it with the parent. Parent has to be smaller. This case it's not. So I swap. Compare with the parent. Parent has to be smaller. Parent is small. Okay, now we're good. So the bubbling up is over here now for this number. Next number. 88. Put it here. Compare with the parent. Parent has to be smaller. Okay, we are good. So we can similarly continue adding more numbers where the parent has to be always smaller. So 6 is smaller than these two. 10 is smaller than this, 10 is smaller than this, 17 is smaller than this, 17 is smaller than this. So we are good. So this is how you do insert, and you can see that the smallest number always comes to the top. So find min will give you the smallest number. Now next operation after insert is remove. Now if I say I want to remove min, how do you do that? So the way to do that is you remove min number 6 and you take the last number and put it in its position. So I take here, put 88 here, okay? Now we will do something called bubble down. So previous insert we did bubble up, now for remove we do bubble down. So bubble down is the opposite. Here what we do, we compare it with its min child. So whichever is min, we swap it with that. Okay, here compare it to these two. 10 is smaller and 10 is smaller than 88 also, so that we swap it. If it's not smaller, then you don't need to do that. 88, 10. Again compare it with the min child. Compare it with these two. This is the min child. Is it bigger than the min child? Yes. So we have to swap it so that the parent is smaller. 35, 88. So now again the binary heap property is met where the parent is always smaller than the child. Parent smaller, and you can again do remove min quickly, like you notice 10 came to the top, which is the minimum. So this is insert and remove, and both insert and remove are big O of log n. The reason is big O of log n is for a complete binary tree, the number of maximum levels you have to go is the depth of the tree. So like suppose I start here, if I'm bubbling up, this is how much I have to go, which is the depth of the tree. Similarly for remove, if I have to remove and I put like the item, put it here, I have to bubble it down. Again, the maximum work you have to do is the depth of the tree. Like it will come here and it will come here, which is the depth. And the depth for a complete binary tree is log n. So that's why both insert and remove are big O of log n. Now, this covers the basic binary tree, and in a binary tree, basic binary heap. In a binary heap, you also generally maintain the size, the maximum size, the maximum number of items that you have, not maximum, the total number of items that you have. You keep a track of that also. So you can also have an additional here, say get size. So you will need that to iterate, like as long as the size is bigger than 0, keep removing items. So that is one use of it. So one more thing I wanted to cover is bottom-up heap construction. So what bottom-up heap construction is, if you are adding numbers one by one like we did here, the total complexity is n log n, right? Because for n numbers, every insert is log n. So for n numbers, your total insert time will be n log n. But suppose you are not getting the numbers one by one. Instead, in the beginning of the program, I give you like these 10 numbers and say, this is create a binary heap with this. So in that case, instead of n log n, you can actually do it in time n. And the way to do that is you just put the numbers in the order you get it. First you do it that way. So say you get like that, right? You get 10, 100, 20. So you put it in whatever order you're getting it. 120, 35, 6, then 1788, then 10, 11. So let's stop here, 10, 11. So now the way you do it for bottom-up heap construction is you first put all the numbers in whatever order you're getting it, and then start from the last inner child. So start in last inner child means it should not be the child, it should have a parent. So that's the last inner child, which is this guy. So you ignore these. Start with the last inner child and then you bubble down from there. So 35 you compare to 10. If this is 10 is smaller, you swap it. and then you go to the next one, which is this guy. Again, do the same thing, bubble down, then go to this one, again compare it with this children, bubble down all the way down, and keep doing that. And you start from this last inner child, do that for all the nodes, bubble it down, and then the total time taken is big O of n instead of big O of log n. So that is bottom up heap construction. So that is pretty much what I wanted to cover in today's lecture. Alright, thank you.